Hello everyone, so myself Upadhyay and I'm a member of IPC Early Builders cohort. So I apologize in advance, my slides are not as cool as Helen's. So I'll just go ahead and talk about data zen. So we at data zen are trying to bring compute to the storage, not the other way around. So let's talk about the problems with the current existing systems, protocols in the compute ecosystem of Filecoin. So the architecture looks same with every computing protocols such as Fluence or Bacalhau and others. So what they do is first they fetch the data and run compute on it. So the problem arises at this point where they fetch the data. So this can lead to many problems such as compromised data sovereignty, because when you fetch the data, you are never sure that the third party who's performing the computation can lead to data leaks. So we can't trust them with sensitive data. So let's say you have some financial statements uploaded and some DeFi protocols needs to perform computations on this data. So you can't fully trust them to, as in share the data to a third party compute service such as Fluence Nodes or anyone. So yeah, so that's the problem over here. Now the second one is slow computation. Of course, adding a step of fetching the data from a storage provider can lead to many different problems, such as the storage provider not being online at that time, the storage, the latency in the data fetching. But what if we can like eliminate this step altogether of data fetching part? So there's no sufficient data access control. Let's say I have financial data statements. I only want the compute providers to access the amount part of that data. So as a data provider, I can't place restrictions on the specific portions of the data that can be accessed by the compute provider. And also, Fluence has done a pretty good job to overcome the slow computation part using cloudless servers. But they also introduced some new steep learning curves, learning new languages to perform computation from developers' point of view. So DataZen is a new L2 built on Filecoin that will be inheriting all the good features of the compute and resolve all the problems I mentioned before. So yeah, we'll be building on top of Filecoin existing architecture. We'll just add a compute layer on top of that. So the Zen node, as we call it, would be a combination of storage nodes plus the compute node. So what we'll do is create an additional built-in actor using IPC that tracks the state of compute. So currently, Filecoin already tracks the state of data storage, right? I mean, the proofs are uploaded during the specific intervals. So we'll do something similar related to compute, specific states of compute, like the compute has been requested, the compute has been approved, processed, or and release the rewards accordingly. So introduction of an L2 token. So a layer 2 token defill, which will be pinned to Filecoin, thus inheriting all the crypto economic features of the Filecoin and extending on it further as a unified reward token for compute as well as storage jobs. So how would we onboard the Zen providers, the unified providers of storage plus compute? So what we'll do is, as Filecoin already does while onboarding the SPs, they check the available system requirements and everything. And we'll also, for the compute portion, we'll use the proof of compute. And as we saw in the last presentation, that the compute units proof everything is generated using Fluence. So we'll do that and club it with the storage and the storage requirements proof and onboard the Zen provider. Now, why does data Zen make sense in means introducing something new in this ecosystem? So let's talk about different actors at play here. First of all, it's data provider. Let's say I'm a data provider. I wanna store some data so that users can perform compute or just store it. Like it's the nodes are compatible for both of them. Like you can just store or you can post an ad for the compute. So it allows us to enable the data sovereignty on the data. So we know that our data won't be uh, leaked during the process of compute, because for highly sensitive data, we are planning on, so I'll explain it over here. So let's say you have a data.csv. So you'll be using datazen client. So it can be a CLI or a web interface. So we'll be encrypting that data. Now the encryption can be performed in two different ways depending on your requirement. Let's say I have a highly sensitive data, financial statements of a company. So what I'll do is I'll go with the fully homomorphic encryption part. So in this case, even the Zen provider, that is storage plus compute node, won't be able to access my data, but it limits the amount of computation that can be done on the data, and it increases the computational resource consumption. So that's something we have to keep in mind. But for normal use cases, we can just normally encrypt it using AES symmetric and asymmetric encryption. Now let's look at the POV of compute client. How does a compute client perform computation? So a compute client can come on our platform, choose and data add. He can choose multiple data adds. Then he has to provide compute collateral so that he doesn't use the computation overhead. Then the Zen provider performs computation for the compute client. And between here, every steps, the proof is uploaded to the IPC L2, and the state of the compute is maintained on chain. So yeah, so after the computational results are out, the data adds chosen by the compute client would be given rewards along with the Zen provider, some portion of the data. So yeah, that's all from me. I guess it was a pretty small one, but yeah. Currently, we are just starting. I mean, I'm all the team. Yeah, I'm going solo. So we are open for collaborations. Hit me up if you want to collaborate, or yeah, just chat. Thank you.